In this video, we're going to look at probability. We want to understand some terminology involved with probability, be able to calculate a simple single probability, compound probabilities using and or, and also conditional probabilities. So just looking at some basic terminology, the sample space is the set of all possible outcomes from an event. So let's say we're rolling a single die. Then our sample space would just be 1, 2, 3, 4, 5, and 6. So what are all the possible outcomes that can happen? An event is just a subset of the sample space, which could be the entire sample space. So maybe our event E is rolling even. So then our event E would be 2, 4, and 6. And then the probability of an event is simply the number of ways that the event can happen divided by the number of outcomes in the sample space. So if we say what's the probability of rolling that even number, then we had 3 events in the event space and 6 events in the sample space. So we get 3, 6, which is 1/2 or 0.5. So your probability can be given as a fraction, a decimal. Technically, you could also give it as a percent, so we could say 50%. If you do a fraction, you should reduce. So remember, use your calculator, and you can help. That will help you reduce. Okay, a few other words that we need to understand is. Okay, so first we have mutually exclusive events, which are events with no outcomes in common. Visually, that might look like this. So this is our sample space, and this would be event A, and this would be event B. So if we're looking at it visually, there's no overlap between the two events. So next we have independent events, which are 2 events where the probability that the second event occurs is not affected by the outcome of the first event. So for example, if you're tossing a coin, you toss that coin and it comes up heads the first time. The next time you toss the coin, it's still a 50% probability that you get heads again. So those are independent events. If you're rolling a die and the first time you roll a 4, the probability that you get a 4 the next time is still 1/6. So the events are independent. The outcome of the first event doesn't change the probability of any of your second events occurring. So next we have conditional events or dependent events, and these are 2 events where the probability of the second event occurring depends on the outcome of the first event. So if you have a deck of cards, for example, and you choose a card, the probability that you get an ace is 4 out of 52. If you pull that first card out and you don't replace it, then the probability that the second card is an ace depends on whether or not you have an ace in your hand. So if there's an ace in your hand, the probability the second card is an ace is going to be 3 out of 51. But the probability that the second card is an ace if the first one's not an ace is 4 out of 51. So the probability changes depending upon the outcome of that first event. There's notation for conditional probability. So if we do the probability of A and then a vertical line and B, this means the probability of A given B. So this means what's the probability that event A occurs given that we know event B has occurred. All right, so if we're looking at the probability of event A or B occurring, then we have to say this is the probability of A or B. Generally, when you're doing counting or probability, or means add. So this is the probability that A occurs plus the probability that B occurs minus the probability that both A and B occur. So we can't count anything twice. So if an event is contained in A and in B, then we've counted it in both of these probabilities, so we have to subtract it out one time. So this is called your general probability formula. Probability of event A and B occurring is going to be probability of A and B. And tells us that we're going to multiply, so this is the probability of A times the probability of B. Here we have a condition, and this is that A and B are independent events. And then we have the probability of event A given that event B occurred. So the probability of A given B is the probability that A and B occur divided by the probability of B occurring. So whatever is your second letter here is your given condition. That's what goes on the bottom in the denominator here. All right, so if we look at some examples here, we have what's the probability of drawing a 5. So here's my 5s, or a 10. So here's my 10s from a standard deck of cards. So first thing I want you to notice is that that's an or there. So this is the probability. What's the probability of 5 or 10? These are mutually exclusive events because there's no overlap between the 5 and the 10. And then remember that or tells you that you're going to add. So the probability of 5 or 10 is the probability of getting a 5 plus the probability of getting a 10. So there's 4 5s out of 52 cards, plus there's 4 10s out of 52 cards, which gives me 8 out of 52, which is 2 out of 13, or 0.153. So remember, or means add. We can never count anything twice, but there's no overlap between those two, so we don't have to worry about it. So similar question, what's the probability of getting a 7 or a diamond? So here we're looking, okay, so my 7s are here, and then my diamonds are here. So notice now there's overlap between those because this card is highlighted in both colors there. So again, though, this is an or question, so the probability of 7 or diamond, but these are not mutually exclusive events. So my probability of 7 or diamond is the probability of 7 plus the probability of a diamond minus the probability of 7 and diamond. So here there are 4 7s, so 4 out of 52, plus there are 13 diamonds, so 13 out of 52, minus there's 1 7 of diamond highlighted here in yellow, so 1 out of 52. So this is going to give me 16 out of 52, which will give me 4 out of 13, or 0.3077. So again, or means add, but here because we had overlap between the sets, we had to subtract out the overlap. So a card is drawn from a standard deck of cards replaced, and then another card is selected. What's the probability of getting 2 aces? So this is probability that my first card is an ace and my second card is an ace. Because the card is replaced after I choose the first one, then these are independent events. So when I have an and, remember that means that we're going to multiply. So this is just the probability that my first card is an ace times the probability that my second card is an ace. So the probability my first card is an ace is 4 out of 52. We've replaced it, so then the probability of the second card is an ace is also 4 out of 52, which gives me 16 out of 2,704, or 0.0059. So again, similar question. 2 cards are drawn from a standard deck of cards without replacement. So this tells me then that these are dependent or conditional events. So again, what's the probability of getting 2 aces? So this is the first card is an ace and the second card is an ace, given that the first card is an ace. So in order to get 2 aces, the first card has to be an ace. So we have to make that a condition for the second event to occur. So then remember, this is still multiplication. So this is the probability the first card's an ace times the probability that the second card is an ace, given that the first one was an ace. So the probability the first card is an ace is 4 out of 52. So if we remove that card from that first card from the deck, we have to assume that it's an ace. Now there are 51 cards left in the deck, and since the first card is an ace, there's only 3 aces left in the deck to choose from. So this is going to give me 12 over 2,652, or 0.0045. So in general, remember, or means add, but you have to be careful if there's any overlap between the sets, so are they mutually exclusive or not. And means multiply, but you need to pay attention to whether or not the events are independent or dependent. If they're dependent, then that second event has to be calculated in the conditional format. So you choose a card from a standard deck of cards. What is the probability that it's a king, given that it is a red card? So probability of king given red. So remember, we have a conditional probability formula. So this is probability of king and red divided by probability of red. So in a standard deck of cards, how many are red king? So that's 2. So 2 out of 52. Over what's the probability of a red card? So how many cards are red? So that's 26 out of 52. So then we've got 2 out of 52. Instead of dividing by this, we're going to multiply by the reciprocal. So we get 2 over 26, or 1 over 13. Another way to think of a conditional probability is to kind of look at your sample space. So sometimes you'll have a sample space that's small enough for you to kind of just count and look at that sample space. So what is the probability of a king given that it's a red card? So if we just look at the red cards, then we're looking at these red cards, and there's 26 of them. So the given becomes your denominator. So there's 26 cards to choose from. And then from only those cards, how many of them are kings? So we've got 2 kings here. So then that goes on top. That's my numerator. So we get 2 out of 26, which is 1 out of 13, which is the same thing we got with the formula. So in this case, we had a discrete sample space and then we could count it. So it was easy enough to do that. In some cases, you won't necessarily be able to count the sample space or even visualize it. So you'll have to use the formula. All right, so here you choose a card from a standard deck of cards. What's the probability of getting a king given that it is a face card? So here, probability of king given face card. So again, if we use the formula first, we're going to go, what's the probability of king and face card divided by probability of face card. So how many cards are kings and face cards? Well, there's 4 kings, there's 12 face cards. All kings are face cards, so that's just going to be 4 out of 52. So how many cards are face cards? There's 12, so 12 out of 52. And then again, we're going to go 4 out of 52 times 52 over 12, which is 4/12 or 1/3. Again, if we think of this sort of in our visual, given that it's a face card, so these are my face cards, and there are 12 of them. So that becomes my denominator. Of those 12 face cards, how many of them are kings? So those are 4. So I get 4 out of 12 again, which is 1/3. Same thing we got with the formula. In the game of Yahtzee, on the first roll, 5 dice are tossed simultaneously. What's the probability of rolling 5 sixes on the first roll? So remember, when we're rolling dice, these are independent events. So probability of 5 sixes is the probability that the first one is a 6, and the second is a 6, and the third is a 6, and the fourth is a 6, and the fifth is a 6. So remember, Anne tells me that I'm going to multiply. So this is the probability of the first one is a 6 is 1 out of 6. And then 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. So that's going to be 1 out of 7,776, or 0.0013. So again, in the game of Yahtzee, 5 dice are tossed simultaneously. What's the probability of rolling 5 of any number on the first roll? So the probability of 5 of any number is getting 5 1s, or 5 2s, or 5 3s, or 5 4s, or 5 5s, or 5 6s. So remember, or tells me that I'm going to add. So this is the probability of 5 1s, plus the probability of 5 2s, plus the probability of 5 3s, plus the probability of 5 4s, plus the probability of 5 5s, plus the probability of 5 6s. So we know the probability of 5 6s because we just calculated that, and that was 1 over 7,776. The probability of 5 5s or 5 4s or 5 3s or 5 2s or 5 1s is going to be the same because the probability of any number is the same, so we can kind of fill all of these in. So if we add those up, we're going to get 6 over 7,776, which is approximately 0.00077. All right, so here we're going to consider a game where a 5-card hand is dealt. What's the probability the hand contains all spades? So if a 5-card hand is dealt, you're being dealt a card, and that card is not being replaced, and you're being dealt another card. So these are dependent events. The probability of all spades is the probability that the first card is a spade, and the second card is a spade given that the first card is a spade, and the third card is a spade given that the first 2 were spades, and the fourth card is a spade given that the first 3 were spades, and the last card is a spade given that the first 4 were spades. So each time my probability is going to change. So remember, Anne tells me I'm going to multiply. So we're just going to multiply all of these together. The probability of the first card's a spade, and then the second one's a spade given the first one was, and the third one given that the first 2 were spades, times the probability that the fourth one's a spade given the first 3 were spades, times the probability of the fifth one is a spade given the first 4 were spades. So the probability of the first card is a spade is 13 out of 52. The probability of the second card is a spade given the first one is a spade is going to be 12 out of 51. So there's fewer cards in the deck, and there's fewer spades in the deck. And then the probability that the next card is a spade is going to be 11 out of 50, and then 10 out of 49, and then 9 out of 48. So we end up with about 0.000495. Another way that you can look at this when you're dealing with cards, so dependent events, where order does not matter, then we can do this using combinations. So the probability of 5 spades could be calculated this way. There are 13 spades in the deck, so 13 spades. We're going to choose 5 of those, and that's what we want to happen. And then generally any hand in the deck is chosen from 52 cards, and we're going to choose 5 of those. So if we use our combination in the calculator, so we're going to put in the 13, go to the probability, do the combination, 13 choose 5, divided by 52, go back to the math, get the combination again, 52 choose 5, and you can see we end up with the exact same answer we got before. So just a preference, whichever one makes more sense to you. All right, again, consider a card game where a 5-card hand is dealt. What's the probability that the hand contains all diamonds? So remember back here, we did what's the probability the hand contains all spades. So this is going to be basically the same question. So we can do it either way. So probability of 5 diamonds. We could do 13 out of 52 times 12 out of 51 times 11 out of 50 times 10 out of 49 times 9 out of 48, which is going to give us 0.000495. Or we could use the combination method that we just did, so probability of 5 diamonds. We could say there are 13 diamonds in the deck. From those 13 diamonds, we're going to choose 5, and my sample space would be choosing 5 cards from the whole deck, so 52 choose 5, and again, we're going to get 0.000495. Consider a card game where a 5-card hand is dealt. What's the probability the hand contains 5 cards of all the same suit? So the probability of 5 of the same suit is either 5 diamonds or 5 spades or 5 hearts or 5 clubs. So remember, we calculated the diamonds and we calculated the spades. The hearts and the clubs are going to be the exact same number that we got for both the diamonds and the spades. So now we just got to think about how to break this apart. So remember, or means that we're going to add. So this is probability of 5 diamonds plus probability of 5 spades plus the probability of 5 hearts plus the probability of 5 clubs. Then remember, we know this was 0.000495, and this one was 0.000495. And this one's going to be the same, 0.000495, and then this one's going to be the same as well. So we got 0.00198. All right, so again, consider a card game where a 5-card hand is dealt. What's the probability the hand contains exactly 3 aces? So we're going to contain exactly 3 aces, and then the other 2 cards can be anything except aces. So we can kind of change that into this. We're going to say probability of 3 aces and 2 not aces. So we're going to make that the probability of 3 aces and 2 not aces. So I know this seems kind of weird, but remember it says exactly 3 aces. So these other 2 cards cannot contain an ace in them. So we can do this a couple of different ways. The first is to kind of use our fractions and our conditional probabilities like we did before, but we have to think about the order of the situation. So we've got 5 cards here, and 3 of them are going to be aces. So the aces could be here, or the aces could be here, or the aces could be here, or the aces could be here. So there's all different combinations that we can create where those 3 aces could be. We don't care where they are, but we have to account for all of those possibilities. So what we would have to do is figure out all of the possible combinations that I can create here where 3 of my spots are aces and 2 of them are not aces. So in order to do that, we would do from the 5 spots, we're going to choose 3 of them to be aces. So what we would have to do is kind of put that into our probability expression here. So the probability of 3 aces and 2 not aces is 5 choose 3, and then for each of these, the probability of an ace is going to be 4 out of 52. And then if the second one's an ace, given that the first one is, that's going to be 3 out of 51. And then the next one is an ace, so 2 out of 50. And then not an ace, so there are 52 minus 4, or 48 cards that are not aces, so 48 out of 49, and then 47 out of 48. Now let's say if we look at this one where it's not an ace and then 3 aces and then not an ace. So now this one would be not an ace, so that's 48 out of 52 times, and then this one's an ace, so now there's still 4 of them in there, so 4 out of 51 times this one's an ace, so now there's only 3 aces left, so 3 out of 50, and then there's only 2 aces left, so 2 out of 49, and then not an ace, well we already used 1 not ace here, so then this is 47 out of 48. So although the numbers are in a different order, we still have a 4, a 3, a 2, and then a 48 and a 47. So the same thing here, if we had ace, not an ace, not an ace, ace, and ace. So this would be an ace, which would be 4 out of 52, times not an ace, so 48 out of 51, and then not an ace again, so 47 out of 50, and then an ace, so 3 out of 49, and then another ace, so 2 out of 48. So again, you can see although things are in the different order, we still have the same 4, 3, 2, 48, and 47 in our numerator, and then my denominators are the same. So it doesn't matter what order these happen in, but I'm going to multiply them together, and multiplication's commutative. So I'm just going to use this first one here. So 4 out of 52 times 3 out of 51 times 2 out of 50 times 48 out of 49 times 47 out of 48. All right, another way that we can look at this question is similar to what we did before with the combinations. So the probability of 3 aces and 2 not aces. So if we use combinations, we can say, okay, well, I need to choose 3 aces. Well, there's 4 aces in a deck, so 4 choose 3. So from the 4 aces, we're going to choose 3 of them. And multiply. And means multiply. 2 not aces. So remember we said there's 48 cards that are not aces, and I'm going to choose 2 of those. And then my denominator is just the general 5 card hands. So from all 52 cards, choosing 5. Then you can see from the calculator here, we got the same answer with either expression. So it's really just kind of a preference, whatever makes more sense in your head. And we're going to end up with 0.0017 for our answer.